Okay, we've already talked about how temperature increases the reaction rate, and I want you to think of it like temperature would increase the rate constant K, which would increase the reaction rate. So, in other words, the higher the temperature, the higher the rate constant K. Another term that we've talked about is activation energy, and you know it's the minimum amount of energy for a reaction to proceed. And it's important you understand that even if the temperature changes, the activation energy stays the same. So in other words, the activation energy is fixed. If the temperature increases, that just means that there's more particles capable of meeting or exceeding the activation energy. Okay, so we know intuitively that there's a relationship between temperature and the rate constant. We know that as the temperature increases, so should the rate constant. Okay, Arrhenius was the scientist who quantified this relationship and came up with this formula here. And this formula states that the rate constant K is equal to this large A, which is the Arrhenius constant, and that's yet another constant, and that constant, big A, that refers to, well, it's a number between 0 and 1, and it just refers to, of the particles with a high enough energy, how many are going to have a successful collision. So if the constant large A is 1, that means that all of those particles will have a successful collision. Okay, if the constant is 0, it means that, well, although they may have enough speed and they might be colliding, they're not colliding successfully. Okay, and well, some of you math geniuses can probably use this equation. It's a little bit complicated just because there's an exponent which includes a fraction, so it's a negative fraction as an exponent actually. It's a lot easier if we can get rid of that exponent, and so how we do that is we take the natural log of both sides. When we take the log or the natural log, it basically gets rid of our exponents. So just as an example, up here, 3 to the power of x equals 10. That's actually a pretty difficult thing to do in your head. It's going to be some crazy decimal to solve for x. However, if we take the log, or the natural log of both sides, here's what we would get if we take the natural log of both sides. Now the natural log of 3 to the power of x is the same as x natural log 3. Now we're in a position where we can isolate the x. And we can punch that into our calculator easy enough to find the answer. So it's similar with the Arrhenius equation. We want to get rid of this crazy exponent, so we take the natural log of both sides. One thing you might have noticed is the small e, which is right there. That's the natural log base e. And in case you're wondering where it went to when we changed this equation, we could have put it in here, natural log base e, but if you punch that in your calculator, you'll see that the natural log of base e is just 1. So because it's equal to 1, we just crossed it off and it doesn't need to be part of our equation. So it's not critical that you know how we arrived at this equation, and we don't need to know how to derive Arrhenius' equation. We just need to know how to use it. So I just thought it would make a little bit more sense to you if you sort of knew how we arrived at this. Once we get to this point, we can rearrange the equation another way, and you'll notice that we've got a couple of constants here. There's a constant, there's a constant. The activation energy is a constant, and the R, which is the universal gas constant, also a constant. So this is fixed. What's changing is the temperature, and so this actually looks like the equation for a straight line. Along K would be Y. The negative activation energy over R would be the slope, M. Reciprocal of temperature, in Kelvin, by the way, that's important, is an X, is X, so Y equals mx, plus B. So then the y-intercept then would be the natural log of A. So you're going to do problems a couple different ways. One, graphically. So you could graph the Arrhenius equation and use the slope, m, to give you the activation energy. So also, if you were to graph that straight line, you'd be able to find the y-intercept, and then that would give you the Arrhenius constant as well. Okay, the other type of problem, which you'll see in the next example, is let's say you carry out the reaction at one temperature and get the rate constant K for that temperature, and then you carry out the reaction. My daughter hates it when I do chemistry without her. So what I was saying was, because we're talking about the types of questions that you would get, and it might be a graphical question, or it might be a question where the reaction's carried out at two different temperatures, and you're asked to calculate the activation energy. Well, we can use this equation twice. And the natural log of A, that's the constant. That's not going to change at either temperature. So if we think of it like, let's rewrite this. The natural log of K at the first temperature, and that's plus the activation energy over RT, and that's going to be equal to the natural log of A. Well, this isn't changing even at the next temperature. So so if we write that out, natural log of the second temperature, K2, plus the activation energy over RT, that's also equal to the natural log of A. So in other words, this equation and this equation are equal to each other. So if we know the rate constant for the two different temperatures, we can work to solve for the activation energy. Okay, and that's what some of these practice problems are going to have you do.